Hey everybody, and thank you for joining us on today's webinar looking at quantifying the thermal touch performance of materials, measuring cool touch and warm feel. I'm Jarrett Nickerson, Commercial Director at C-Therm Technologies. I have our application specialist here with us today, Arya Akamin, who's going to take us through some of the detailed case highlights of these warm feel, cool touch property measurements. Just before we dig into the details, I'll give you a brief overview about C-Therm. At C-Therm, we help research and development and quality control quantify the thermal performance of materials. And the way this is done is through a variety of sensor types. Today's focus will be on the Modified Transient Plane Source technique, which is referenced in ASTM D7984. But we also have other sensors available for thermal measurement of materials. I'm going to give a brief overview of what those look like. So the three main products in C-Therm's lineup start with the TC kit. This kit is for typical academic researchers that are looking to get initial thermal heat transfer data on their materials. Requires a 2-sample setup with the sensor sandwiched between them. It's not aligned with any industry standard or ISO standard, ASTM standard, and can be plug and play with a standard Keithley source measure unit, but is a really great introduction to heat transfer and the study of heat transfer with transient techniques. Our premium platform Trident thermal conductivity. In the middle, we have our pyramid-shaped Trident platform. This allows you to drive the multiple methods that I mentioned in measuring thermal conductivity and also thermal effusivity, which we'll be speaking most about today in understanding warm feel and cool touch. Here you have a needle probe for measuring polymer melts or large particle gravel, soil. You have the ISO 22007-2, which can provide some nice complements for things like thin films or testing polymer materials or porous ceramics. And then, of course, the MTPS, Modified Transient Plane Source technique, which is a single-sided measurement and allows us to take effusivity measurements of textiles, fabrics, and lots of different materials. On the far right, you'll see our TX Touch Experience platform, which is a dedicated unit for testing textiles and fabrics according to the ASTM standard. And what you see here is the compression test device that allows you to properly change and understand the effects of compression on your material that you're testing effusivity and conductivity. So if you're looking for a broad research platform for things outside of just textiles and fabrics, Trident can be a platform that you look at. If your main focus is textiles and fabrics and focusing on the ASTM standard, TX is where we would lead you to. Before we get into warm feel and cool touch, I'll talk briefly about Trident. This is employing 3 different methods with the idea that when it comes to thermal conductivity and understanding heat transfer of different materials, it's best to have options, both for varying temperature and sample type. And that's why we have the Flex double-sided sensor, the needle probe, and the MTPS sensor on this platform. With these multiple sensor options, it allows us to explore different environments and sample types, like testing powders under compression, different materials at high pressures, up to 137 bar, small volumes of different fluids, engine coolants, and liquids, and of course, compressible materials with MTPS for warm feel, cool touch, and insulative materials. The TPS technique affords us a method for some specialty applications. So this includes devices for testing up to 500 degrees C under varying amounts of direct compression and also in testing thin films. And Arya is going to take us through a little bit about how thin film testing can be applicable in the textiles and fabrics industry as well. These specialty utilities under TPS also include slab for very thin sheets of metal and an anisotropy utility that allows you to understand directionally dependent thermal properties of materials. But today's focus will be around the TX Touch Experience platform in measuring warm feel and cool touch. This includes the controller to drive the sensor, MTPS sensor, which is underneath this neat punch out of the red textile here, and control the compression over top of the device. In terms of effusivity range, you have from the effusivity of air around 5 watt/second-half over meter squared Kelvin up to the effusivity of water, so a fully saturated textile at 1600. This can be introduced into a temperature range from -50 to 200 degrees C. And there's little to no destructive nature of this testing. This is simply a material being placed over top of the single-sided sensor. Accuracy, that means testing of known materials, is better than 5%, and precision, or the relative standard deviation of multiple tests, is better than 1% with this method. This is an up-close picture of the MTPS sensor. You have a platinum alloy coil on a ceramic substrate that's covered in a glass coating, which gives it this green hue. Now, surrounding the coil, there's also a guard ring. And during a measurement, there's a heat pulse that's generated by both the coil itself and the guard ring, which allows us to take a through-plane test of the thermal properties of the material. And Arya will talk a little bit about the principles of operation in more depth shortly. So what exactly does it measure? Firstly, we have thermal conductivity, or the rate of heat transfer over a temperature gradient expressed in watts per meter Kelvin, and effusivity, which relates to warm feel and cool touch, a property of the square root of thermal conductivity, density, and heat capacity. You get both of these measurements with the MTPS sensor, and today's focus will be on the effusivity portion with relation to the ASTM standard. There's qualified labs all over the globe that offer testing with ASTM D7984 from Bureau Veritas, Axle Products, and Group CTT in North America, over to Bureau Veritas in Guangzhou in China, and TTRI and Intertech in Taiwan. Statement from one of our most premium users, you could say, one of the biggest brands in the world. The device is working perfectly. Dr. Christian Hyde, working with the Futures team at Adidas in understanding how warm feel and cool touch affects the perception of a person that's wearing different Adidas products, clothing, shoes, these types of things. And when is effusivity helpful? Well, Arya is going to dive deep into the data, but from an initial standpoint, you can think about how does a fleece or a pullover feel for active wear in winter weather? You want it to feel cozy, you want it to feel warm. Well, that's low effusivity. Understanding one of the biggest industries in the world, which is diapers, and how the feeling of the diaper changes when wetted is extremely important and useful in the development of baby care products. So looking at the effusivity changes of diaper materials under wetted conditions can allow you to benchmark different brands of diapers or different innovations in different layering of materials and phase change materials that will ultimately affect how that diaper feels on the baby's skin. And with a 1-year-old at home and a 3-year-old that's now well out of diapers, this is one that's near and dear to my heart for sure. You always want your baby to be comfortable. And lastly, one we can all relate to for sure is when you get inside of a vehicle, what does it feel like when you touch the steering wheel? Well, on a hot summer day, if it's black leather, it's going to heat up. This can change effusivity properties and thermal properties. You can think about this interior where you have a polished wood. How does that feel when you touch the dash? Matching that effusivity to an imitation polymer, which typically feels cooler to the touch. This is where effusivity can help in the automotive industry. And lastly, I'll just point to the ASTM standard D7984. C-Therm is the only manufacturer of the MTPS Modified Transient Plane Source technique under a variety of patents in North America and Europe. And this is specifically listed under this standard. So it's important that if you do want to do this testing according to the standard, that you're working with us at C-Therm or our many partners around the globe. So at this point, I'll hand things off to our application specialist, Arya Akimian, who's going to take us through some case studies and data. And then we'll open things up for questions at the end. Over to you, Arya.
Awesome. Thanks, Jay. Alrighty, folks. So let me just bring up some slides here. All right. Yeah, so as Jay mentioned, again, today's webinar will be focusing in on really quantifying what warm feel and cool touch can mean and what information that gives you. We'll do a little bit of some background on the measurement using MTPS and effusivity as a thermal property, as well as going into some individual case highlights, some from industry, others internal, and some from academia as to how the MTPS is being used in this application space. So, starting out, why is thermal effusivity important? I mean, you can see it in marketing and different areas where groups will be making these claims about the performance of their material, whether kind of the images that Jay showed earlier, if it's a cold weather application where you want to stay warm, or maybe in the gym where active where you're trying to keep cool during your workouts. Being able to make these claims is really beneficial to back them up with some numbers, some values, and this is where effusivity becomes really a critical performance attribute for a number of these products in industry. So what is it? Now, effusivity, thermal effusivity, defined as a material's ability to exchange heat or thermal energy with another body that it's in contact with. So you can imagine here in really the examples that we're talking about, textiles is the two bodies. In this case would be the hand or the human skin that's in contact with that fabric or textile material. As mentioned earlier, it is related to thermal conductivity. These are two related properties through the density, heat capacity, and specific heat. And when we're talking about effusivity, we are working in units of watt second to the 1/2 meters squared Kelvin. So, just in an example here, this is one that I use to help people visualize or experience effusivity in kind of your day-to-day environment, maybe in the room or the office that you're in right now. But if you looked around, I'm sure you could find two different materials, whether it's a metal on the chair that you're sitting on, maybe the wooden table, desk that you're working at. Really, both of these, any material in that room should be approximately the same room temperature, the same ambient condition, assuming it's not part of a heat source or some kind of external device. Now, even though they're at the same ambient temperature, when you go to touch those two different materials, you'll most often find that they feel or they're perceived as feeling different. And this can really come back and directly relate to the thermal effusivity of that sample. So obviously the higher effusivity material, such as a metal, will feel much cooler to the touch than perhaps a wood or a polymer would be. And this same idea here can be brought into the field of textiles and looking at the different types of textile materials, products, and how that relates to those samples. So effusivity and touch perception, there is a clear correlation. This has been documented, and there's current work being done on this as well. But we have been able to show that metals, higher effusivity materials will feel cooler to the touch and have a cooler perceived feel than, say, your polymers compared to your woods. And then this can kind of scale through the different range of materials that you're working with. So there is a clear correlation here. And really the use of effusivity over just the traditional touch panel really brings you into an area where you can quantify some of these values and not so much relying on the human touch perception, which can have its own set of biases. So really being able to quantify this is really the main driver behind using effusivity as the overall guiding metric. So as you can see, this is just an example, product index that we've built out over the years. You can see on the left end, the warmer feeling materials anchored at the low end from air. Obviously looking at an example like a fleece material, feeling more warmer. And then as you move more and more to the right, getting into some of those cooler feeling fabrics. And then when you get to the extreme end where you're dealing with semi-saturated or wetted textiles, those would feel the most cool to the touch. Now, these are just examples. There are, scenarios where kind of see a cotton t-shirt there, 100% anchored around 200 effusivity points. This is just a singular material example because there's a lot of things that will influence the effusivity of a material. Whether you're looking at a natural cotton, synthetic, the overall weave pattern, so how those fibers are all tied together to make the overall fabric, the size of the fiber, lots of different aspects to the overall material design will have an influencing effect on whether it's warmer or cooler feeling to the touch. But really the star of the show here and what we're going to be focusing on for the driver from a lot of the data that we'll be presenting is really the TX Touch Experience platform. Jay mentioned it earlier, but really this is the system and configuration that employs the MTPS sensor for the driving measurement of effusivity. Really, if you do look into the standard ASTM D7984, there's a lot of information in there on proper test setups, conditions, things of this nature, but it does specify the use of the MTPS sensor and the MTPS alone. So really, if you are looking to conform to this standard, this is the setup that would be being used. So not going to dive too deep into the theory, but just a nice high-level look here. Principles of operation. When we're dealing with a transient-based measurement, they work off a similar idea regardless of the method in that you're delivering a known amount of heat to the sample sensor interface, as we can see here in that top left image through the internal sensor coil. So that heat is delivered to that sample, and then the sensor is simultaneously monitoring the change in temperature, or you could view that as the change in voltage that across the circuit that occurs over time. Now, in this kind of heightened example here with two very different materials, a foam, something very low in effusivity, low in conductivity, will result in a much steeper rise in temperature if you kind of were to dive into the raw data. Whereas a metal, for something higher in performance, would be much flatter as it's much better at dissipating that generated heat. So this is the core idea behind the measurement. You're monitoring that change in temperature that occurs over time. Jay did mention this earlier, but I'll focus on it a little bit here as well. The guard ring, this is essentially a technology that's only available on the MTPS, and it surrounds the entirety or the contour of the sensor itself. Now, when that initial sensor fires or initializes for the measurement, the guard ring will initialize simultaneously. And what this does, it prevents any of that lateral heat loss from occurring. So your measurement is always going to be directionally dependent going into the material that you're testing. And this will depend on obviously the way you're orienting the sample on top of the sensor to determine the direction of that measurement into your sample. It will always be normal to the sensor surface. And lastly, with the MTPS, it is one of the, call it the simpler methods to operate. There are other methods that require the use of manually setting up your really your timing and power parameters for your measurement. This is really at the core of the two main parameters that can be adjusted in a conductivity measurement. But with the MTPS, it's all factory calibrated, very simple plug and play device. You simply select the appropriate calibration you want to run with based on the material type. And there is a specific textiles calibration developed for those materials. Simply select that, set up your samples, and run your measurement. There is no real parameters that need to be adjusted or played around with. And there is no linear regression or post-data analysis required. Everything is very simplistically laid out for you. So coming back to, more looking at textiles and what factors really influence your thermal effusivity. So we're talking about general materials, really temperature, humidity. Those are two environmental factors that will be very important to, one, control for, but also, take note of during your testing. Generally speaking, they will influence the thermal properties of any material. Some are more sensitive to others, but really temperature and humidity should be controlled. And if you are looking to test specifically according to the ASTM D7984 standard, there are guidelines in there on the acceptable ranges for those two parameters. Now, density, this is something it's really dependent on the material that you're testing. So you can imagine a lofty, down-filled jacket would obviously be much less dense than kind of a plain sheet of fabric. So there are differences in density that will influence the overall measurement, but also the density that you're essentially imparting on the sample. So how much you're compressing the sample by. If you recall, there was the image of the compression test accessory, the CTA device, which can be used to apply varying force loads on top of your sample material. And for any samples that are compressible in nature, like most textiles, fabrics are, the extent to which you're compressing those samples by will have an influence on your measurement. And again, the setup and the parameters that are required to get repeatable and accurate data are all outlined in the ASTM standard. But it does give the option to also do some more perhaps research testing, maybe going outside of the standard, looking at how different conditions and different setups can influence the effective measurements of those samples. Now, diving into textiles, obviously, really a lot of different aspects can influence the measurement. So in the example, we kind of have this natural cotton picture in the middle there, but that singular material could be taken and have weaved into different fiber sizes. Those fibers could then be made into different pattern materials. And even though you're starting from the same base product, which at its core would have a base property value, how you treat it and modify it and change it to make these different textiles and products will change the overall measurement that you're going to observe when you do your testing. So there's a lot of different parameters, obviously, that go into textiles. Textiles are a very complex material, as you can imagine, getting into all these different variables, but they all come into play to affect your overall measurement. Again, just kind of coming back to the ASTM standard here, really when we're talking about this industry, really standardizing your method to ensure, comparable, reproducible data is obviously really important, whether you're on the product and, taking those materials, developing them into final products for your companies, or maybe you're on the supplier side, looking at sourcing different materials and using those and bringing them into the product line for other companies. Being able to really compare your results apples to apples is going to be really important there. So like I said, the ASTM standard really outlines a lot of information on your overall test setup, environmental conditions, things like this. Just, the two big ones that I always come back to are temperature and humidity. So these are the kind of the requirements as outlined by the ASTM standard. So your temperature range, 21 degrees plus or minus 2 degrees Celsius, with a relative humidity of 65 plus or minus 5. So that's kind of your general guidelines for your test conditions as well as your sample conditioning. So just as an idea, that's approximately where you'll want to be operating in when testing according to the standard. So really the next little bit of our talk here will be going through some different case highlights, examples, and really coming back to the core of fabrics, textiles, and the touch performance properties. So starting out here, just have an image here of Mark's Work Warehouse. This is a company that really helps spearhead the standardization effort back in a few years back now, really looking to finding a way to take these various products that they had and quantify them based on the thermal performance or the thermal properties of their sample. So, example, looking at this kind of a warmer feeling undergarment where they were trying to really find a way to best quantify that material. And really this helps spearhead a lot of the effort that was behind using the MTPS and standardizing according to ASTM. Now, as a kind of an example, some of the work that we did initially was looking at helping, qualify material selection based on the end use application. So an example here, looking at a thermal fleece. This was, obviously hoping to be, used for a more warmer feeling application. And then there's 3 other fabrics, different polyester blends, some that have nylon in them, different weighting, different description of the overall, the mesh design. So we're looking for a way to really help quantify these and kind of establish a baseline for product comparison. And this is really where MTPS became of value for them in the effusivity space. So you can see that a thermal fleece here was coming in at the low end, which had that more of that warm feeling material, and then the other samples you see had a range on the lower 100s to kind of the upper, and they were all used in different products depending on what they're looking for. But this is just kind of that singular example as to where a lot of this work started from, and obviously over the years it's really grown from there. Some of the other more, I call them more specialized testing, has been a lot of groups dealing with various coatings on their materials and their fabrics. Some of these coatings are to, for, various treatments for other aspects of the product performance, but some of them are directly related to the thermal sensation or the thermal feel. One of them here is the influence of using a PCM or a phase change material as a coating on top of a mattress type sample, in the hopes to see that if the treated versus the untreated sample ended up showing any significant difference, and how that would affect the overall performance of that material in its real world application. So as you can imagine, mattresses, one of the main things that you don't want to be when you're sleeping is overheating or too warm. So trying to have this cooling sensation technology being built in directly into that material itself. And again, as a singular example here, some of the materials that were tested, both treated and untreated, you can see quite a significant difference in the overall thermal effusivity measurement. So it's the same fabric with simply a different coating, or one with and without a coating, and you can see how that affects the overall thermal performance of that sample. So really coming back, another big one here is compression. Materials that are influenced by the effective load that you're applying to the sample. Fabrics, textiles are 2 obviously main ones that we'll be focusing on today, but also in like other spaces, whether you're looking at powder beds, there are various materials that are compressible in nature, and really being able to test them in a more representative condition towards the end use application or the real world scenarios is really valuable for a lot of researchers. And with the single-sided MTPS, it really gives you the most control over doing these types of test setups. There are other methods out there that can test these varying properties, but when you're looking at a compressible material, really having control over that compressive load and being able to account for that is going to be really important to get the best overall data. So with the MTPS and CTA, it gives you a very simple and easy way to do that. So when you are dealing with something that's extremely compressible, and kind of this example here, you can see it's like a filler material that you might see in a jacket or some other product like this. you can imagine that as your sample thickness decreases, you're going to essentially be increasing the density or the localized density, in this case over the measurement area. Through the increase of density, this decreases the overall thermal resistance that's in the sample, and this results in an increase to your thermal conductivity effusivity measurement. So you kind of see how these properties all play together and influence your overall measurement of that sample. Really, so the performance of as a function of compression, you can see that as you increase the compressive load, therefore resulting in a thinner or decreased sample thickness, this will result in an overall higher thermal measurement, in this case thermal conductivity as the metric, but this can be scaled through for effusivity as well, depending on the material that is being tested. The effect of the sample's compression load will influence the overall measurement of that material. So this example here is looking at a study of an academic group out of the Czech Republic and Pakistan, looking to characterize the performance of some unconventional knitted fabrics. Now, in this study, really what they were aiming to do is understand the influence of using a singular material type, but with different weave patterns. So in the example here, there's a plain or a single jersey knit compared to a rib or a double jersey knit structure. And using this kind of difference, this one variable being modified, seeing how that influences the overall thermal results. So they had 4 different test candidate materials, each with 2 different knit structures. And they were looking to see, obviously, how these different materials performed compared to each other, but then also how they overall compared when looking at the different knit structures and patterns themselves. Really, at the end of the day, they were able to determine that they were using thermal conductivity as the overall guiding metric here, but they were able to determine that the ribbed knit structures were lower than the plain, therefore having a more warmer feel or cool touch if you relate that to the thermal effusivity of that sample. You can understand this based on the fact that the increased air voids that would be present in the rib knit pattern as compared to the plain, and how that would influence your overall thermal measurements. However, in both patterns, regardless of the structure that was being used, they did notice that the polypropylene-based samples did have the highest overall values. Because, like I said, there's a lot of things that influence your measurement. The base material that is being used, as well as the different knit structures. But across both knit structures, they found that there is a singular material type that did have the highest performance metric that they were looking for. So while the focus today is on effusivity with MTPS, there are some applications where using other transient-based measurements, such as flex TPS, can really be valuable, especially with the added utilities that they do offer. And the one that I'll be highlighting here briefly is on the thin films unit. And really, I've seen a lot of applications in call them smartwear technologies, where they're materials that you're or products that you're wearing, but ever increasing trying to introduce different technology or devices into that sample. So there are different headgear, helmets, hats that have headphones or sound devices in them. Other materials may have different tracking or different technology built into, say, jacket materials. Some have heaters and warming devices built in. So there's ever more new technological advancements being made, and a lot of those materials may be on what we refer to as thin film. So a lot of polymers, a lot of sheet samples that are very, very, very thin are being incorporated into some of these overall products and structures. And using the TPS thin films, it gives you a very simple, easy way to measure the thermal conductivity value of those samples, and you don't require to stack to that minimum testing thickness requirement that's outlined for the MTPS. So you can get away with a much thinner sample here, depending if this is an application that is of interest to you. Now, with the thin films utility, It's obviously working off the TPS, or the transient plane source sensor. So it's a different method. And this would be something that would be available on the Trident platform. But just to highlight, it does offer some of those extended capabilities that may be valuable depending on the research and the products that you're working with. So you can kind of see here just some examples of some data of some different materials that are measured compared to their literature value using the thin films method. And really we see some of the variability max on the upper end of about 10% for some of those samples, but it really gives you the ability to test some materials that are as down as a few dozen microns thick. Whereas in other methods, you would require to have that stacked up to multiple layers, or be testing the bulk sample, and wouldn't be able to get that representative measurement of that thin material. So pivoting back here a little bit towards the MTPS, this is something that I highlighted a few months ago in one of our previous webinars, but I've gotten some questions on it and really wanted to bring it up here again. But the effusivity measurement of a material, in combination with the temperature of the different samples that you're testing, you can use this information to essentially determine that interfacial surface temperature that is observed when you're touching or in contact with various material types. This is really call it the math behind why, per se, a metal would feel cooler to the touch than the wood, as you can see based on the effusivity differences. In the example here on the right, you can see that if you run this calculation, your steel would result in essentially an interfacial temperature difference of around 11 degrees, whereas something much lower in effusivity, such as a carpet or a wood, is much less. Therefore, it's pulling less thermal energy away from your hand, and therefore not feeling as cool to the touch. So there's actually a way to not only quantify the touch performance using effusivity, but also try to understand how that overall temperature difference will be experienced in the actual end use condition here. Now, when we're looking at this equation, there are a number of factors to consider. One of those being is, what part of the human body is actually in contact with the material. What temperature that part is, and things like this, because the human body, the sensitivity across the different parts of the skin do vary across the body. And also with age, there's been some studies that have been published, different parts of the body are more sensitive to these temperature differences than others. And then also it's been shown that as you do age, your overall sensitivity does change and generally decreases. So there are a lot of things to consider here, but if we kind of use a generic kind of baseline of the human hand, it has been shown that the area around the thumb can detect increases of temperature as low as about 0.2 degrees Celsius, and decreases of down as low as 0.11 degrees Celsius. So this can give you a kind of a rough idea as to what types of differences can be detected, and therefore which ones would be significant when you're comparing different materials. So obviously, kind of running through that thought process here, taking a look at how a material, if you're looking at a baseline, so I'm just going to use the example of the thermal fleece, 61 effusivity points. When would a change to that baseline fabric, whether it's through maybe a different material candidate, different treatments, an overall different structure, whatever that may be, when are you going to notice a significant difference in touch based on the baseline or that control sample? And how do you quantify that? Well, if we run through the equation that we showed earlier, we're assuming a few things here, that the materials are at a room temperature of, let's say, 20 degrees, your hand temperature is at 32. And with those numbers, if you run through the equations and you have these example effusivity values, so one sample, that base control was, say, 61 effusivity, sample 2 was 66, and then so on and so forth. At which point does that difference become detectable or significant? So if we use the idea that a decrease in temperature of 0.11 degrees is a detectable difference by the human hand, therefore we can show that you would need to have an effusivity difference of about 15 watt second to the 1/2 meter squared Kelvin to be noticeable. Now, if you run through this this kind of this thought practice and equation on your own, you will notice that the temperature difference between the skin and the sample will influence the overall difference in temperature that is experienced, but also the range of effusivities that you're comparing to. So lower effusivity materials below 100 compared to the 100 to 200 range, 200 to 300 range, the level as to which the differences become significant do vary, and you will have to have different, essentially differences between that control and baseline sample to that new and treated material to get the same level of difference in temperature that is felt. But you can kind of use this to go through some different experimental and studies here. Using the example of a wetted sample. So water is very high in effusivity, approximately 1600 points. So you could, do just the direct measurement of a dry versus a wetted cotton t-shirt, let's say. So the dry cotton t-shirt coming in, let's say 200 compared to the wetted cotton, which would be much higher. But you obviously know that the wetted material feels cooler based on the fact that it has a higher thermal effusivity. But you can actually quantify how much cooler that would feel by using these calculations. So you can see that you're getting about a 4.2 perceived degree temperature difference between the wetted and dried state. Now, when you're dealing with wetted textiles, this is another thing that has come up. There's a lot of variables that will come into the play here when you're doing wetted testing, related to the fact that a wetted material will be continuously changing dynamically over time. So if it's initially wetted, as soon as that fabric becomes saturated, it will begin the drying process, the evaporation of the water, the spreading of water throughout the fibers, pulling water away from the measurement area if you're having that on top of the sensor. A lot of these things will come into play when you are doing these types of analyses. So it's really important that you're controlling for that and taking note of what's occurring during your measurements. So just kind of go through another final example here, again, coming back to the performance and comfort of diapers. This is one that you really directly see how this can be important and related to effusivity. So in the study that was performed, they were looking at some different diaper brands, characterizing the thermal effusivity under different dried and saturated conditions. And then also analyzing the measurement or the performance of that sample at different time intervals after the saturation occurred. So if you do look at the overall essentially diagram or the design of a diaper, they have three main components. There's that top sheet, which essentially is the material that's in direct contact with the skin. Then there's the internal surge layer, and this is what's really the material that's pulling that liquid or that moisture away from that top sheet and bringing it in through the body of the product itself. And then the absorbent core is where that moisture is retained, so it doesn't leak back up into the top sheet and obviously introduce more of that cooled sensation. So by modifying the different materials that are used in the overall structure, this will influence the overall thermal properties of that material type itself. So in the study that was done, there was essentially a no-name brand compared to a leading brand, which obviously had a higher price tag associated with it. And the idea here was to see if there was any distinguishable differences between those two samples, and if the higher price tag really did have a benefit to the overall performance. So you can see in the dried state on the left side there, initially, very minimal difference, kind of a 4 effusivity point difference between the two materials. If we kind of use that example that we had showed earlier, you could really essentially say there's no significant feeling of difference between those two samples or those two materials in the dried state. But when you initially wet the material, so when it becomes saturated, I call it that time equals 0 condition, and it's measured, the wetted or the no-name brand sample had a much higher effusivity measurement, most likely related to the that top sheet and surge layer not being able as adequately dispersing that liquid through the sample through the material of the diaper, and there's more of that cool felt at the skin of the baby there. So obviously, this results in a much cooler feeling sample, and in this scenario here, feeling cooler, it doesn't necessarily better, would generally be a little more uncomfortable. So we can show that, quite a significant difference here in that initially wetted state. Now, after a 12-hour period, you came back and tested the sample again, and we noticed that that difference became a little less significant after that extended time duration, most likely related to the fact that even though initially that, call it the no-name brand, wasn't as efficient as dispersing that liquid from that top layer into the absorbent core, over time, and given enough time to reach there, it did have a more comparable result down the road. Again, fairly similar, but still a little cooler feeling at the end of the day. But this is just a singular example that you can see that really, if you're looking to quantify how a diaper is feeling to the child or the baby as it's becoming saturated, the time at which it would take to reach that drier state or that lower effusivity measurement can be used to quantify the overall performance of that sample. So here's just kind of a singular example of how that could be done. So really that brings us to the end of today's webinar. Again, really focusing here on the textiles and fabrics with the MTPS. Just to kind of give you some updates, if this is of interest to anyone on the line here, the Thursday, March 18th, we will be doing a thermal conductivity focused webinar, specifically looking at the mapping and filler settling effects detection that can be done in polymer composites. A lot of focus on this one will be on the MTPS sensor as well, but now moving out of more of a into the conductivity space. And as well, the following Thursday, there will be a CETERAM focused webinar for thermal analysis and hydrogen materials. This is something that can be registered for at the link that you can see there, or if you message us in the chat box, we'll be able to provide you the links for that as well. So with that, just want to say thank you for listening. A lot of information came at you, so if there was any questions, I'll throw it back to Jay now for the Q&A session, but happy to answer any questions you guys may have.
Thanks a lot, Aria, for the deep dive. I think from a high level, it's really taking out that assumption that something feels cool or warm to the touch, and really being able to quantify it in a way that, from product selection to material selection, at point of sale even, how something feels when you touch it can make a big influence on that product's performance. So thank you very much for the detailed explanation. At this stage, I will stop the recording and we'll open things up. We have a few questions in the chat box.